Okay, guys, we're going to start chapter 9 today. It's titled Intermolecular Forces and Solutions. We're going to start this chapter by talking about intermolecular forces. And then we'll finish up talking about solutions. But I wanted to start with this slide here and ask you a question, guys. Water. Why, when it's on this leaf right here, why doesn't water just cover it and be flat? You can see it kind of balls up here and forms water droplets. But why doesn't water just sit on this leaf and just cover it entirely flat? How come?
Surface tension. Gravity.
Surface tension. Gravity has nothing to do with it, but surface tension does. But it was a good guess. I think I know what you're talking about, but it's not gravity. Okay.
Has something to do with the intermolecular forces.
Intermolecular forces, okay, obviously. So, why does water form droplets and not just cover something totally flat? Well, that's what we're going to talk about in this first half of this chapter. And the answer is water is attracted to itself. One water molecule is attracted to another water molecule. In fact, it's like, think of them as mini magnets. Yeah, perfect. Think of water molecules like little mini magnets, and they like to stick together. And what we're going to talk about today is why water likes to stick together.
So it's like the opposite of a magnet, because magnets.
It is like a magnet. So I think we've all done this before, where we put water. See how many water droplets you can put on a penny without it spilling over? Have you done this before?
Yeah.
Okay, you can notice here that it even starts to bow out over the edge of the penny. Now, obviously, if you put a lot of water, it's going to spill out, and gravity's and the weight of the water is going to win out, and it's going to spill off. But you can even see it bows over the top. So water is attracted to itself. It's called cohesion. Water has cohesion. On the surface of a water, like a lake or a pond or any body of water, on the surface, that water is attracted to itself and it wants to grab another water molecule, and it causes surface tension. And that surface tension is seen in this picture with this spider. Small, insects, or in this case a spider, can walk on water. Their weight isn't strong enough to overcome the attractive force between water molecules here, so it's able to stay on top. Now, of course, we couldn't do that because our weight is more than a spider, and so we'd fall through. But small insects can walk on water, and that's again because water is attracted to itself. It's called surface tension. Does that make sense? So what we're going to talk about today is why there is cohesion, why there is surface tension. Why, when it rains and rain hits the window, does the water ball up? Why does it form a little droplet? Okay, we're going to figure that out today. So let's get started. Please have your chapter 9 guided notes out. As we go through these slides, there's quite a bit to write down. So here we go. I wanted to start by talking about the difference between intra and inter. Okay? So what is the difference between intra and inter? Well, let's start with intra first. So in your notes, you're supposed to write something here. Intra means within. So intramolecular forces are forces within a molecule.
The inter means in between.
Okay, so we've already learned about intramolecular forces. These are the forces inside a molecule. Ionic bonds, covalent bonds, and metallic bonds are examples of intramolecular forces. So these are forces within a molecule. Let's contrast that to inter. Inter means between. So we're talking about the forces between molecules. That's what this chapter is about. Okay? We are going to talk about these intermolecular forces. There's 3 of them that we're going to learn about in this chapter. The first one is dispersion. The second is dipole-dipole forces. And then finally, hydrogen bonding is the last intermolecular force we will talk about. So I wanted to draw a picture up here on the board and ask you some questions and make sure that we've got the difference between intra and intermolecular forces down. So if I draw the most famous molecule on the planet, what molecule is that?
Water.
It's water, okay? Let me see if you remember this. What's the geometry of water? It's bent. Yeah, it's a bent molecule. All right, that's how many water molecules is that? That's one water molecule. I'm going to draw another one here. And then I'm going to kind of circle it just to kind of give it an outline here. So there's two water molecules. Now I'm going to point to different parts, and you tell me whether it's an intramolecular force or an intermolecular force. What about this attraction between the hydrogen and the oxygen right here? That's an intramolecular force. Be more specific. Which one of the intramolecular forces is this? That's a covalent bond. Yeah, it's a bond within the molecule. It's holding the molecule together. Okay, what about this one? Same thing. It's a covalent bond between the hydrogen and the oxygen, and it's holding this molecule together within it. Well, there is, guys, a force of attraction between water molecules. So this would be called a what? An intermolecular force. And that's what we're going to learn about in this chapter. So we'll find out why water likes to be around other water molecules. Before we get into the new stuff, I wanted to review the older things that we've learned about intramolecular forces. So we've talked about ionic, covalent, and metallic bonds. But I wanted to review this. What atoms are involved in ionic bonding? It has to be a metal and a non-metal. So something below the staircase, something above the staircase. What about covalent? Yeah, two non-metals. So two elements that are above the staircase form covalent bonds. And metallic, this one's the easiest one of all. Two metals. Okay. And all of them share electrons between them except for ionic, which transfers the electron, totally transfers it. Okay. We're going to talk about covalent bonds a lot in this chapter, and they share electrons between the atoms. Okay, and we've talked about that before. So let's get to the new part of the lesson. But we have talked about this word before. Electronegativity. In your book, you're supposed to write down the definition for electronegativity. Here it is. So electronegativity is the attraction that an atom has for electrons. So it's this measure of how strongly an atom pulls electrons toward it, toward its nucleus. It's given the name electronegativity. So it's how strong it pulls electrons toward it. The higher the electronegativity value, the stronger the attraction for electrons. So the higher that value, the more strongly it pulls electrons toward it. Okay, so where do you find electronegativity values, guys? On the periodic table. So on my next slide, I've got a periodic table, but if you're watching the video, please get your periodic table out now so that we can know how to find electronegativity values. So here we go. Here's your periodic table. Now if you look at the key here, electronegativity is found right there, which is the bottom right number on all of these squares for the periodic table. So I'm going to quiz you for a second. This is so important that you know how to find these. What is the electronegativity value for carbon?
2.5.
Good. So we look up carbon right here. It's this lower right number, 2.5. Okay, we got it? What about hydrogen?
2.4.
Hydrogen's right here. We look it up, 2.1. Okay, let's do a couple more. What about oxygen?
3.5.
3.5. Okay. What about, I don't know, sodium? 0.9. So 0.9, it's right there. Okay, I think we got it, right? Now remember, the higher this number, what does that mean? the stronger it pulls what to it?
Electrons.
Electrons. It's called electronegativity. So it pulls electrons toward you. If you remember back a few chapters ago, this was one of the periodic trends. This was one of the trends we drew an arrow for, and it's easy to remember. Which way did the arrow go?
That way.
Yeah, it started down here and went up and to the right. So down in the lower left-hand corner of your periodic table, they're high or low? Very low. So francium is only 0.7. If you come up here to fluorine, it's 4.0. So they're higher up toward the right. Okay. This is what really the lesson is about today. It's about polarity. So take a second, and in your notes it wants you to write down the definition for polarity. Polarity is the unequal sharing of electrons in a covalent bond. Now, I think we told you that in covalent bonds they share the electrons between them equally, but that's not true. Okay, they don't share them equally. And the reason that they don't share them equally in a covalent bond is because atoms have different electronegativity values. So the atom that has a higher electronegativity value will pull those shared pair toward it, a little bit more closely to it, and so it causes polarity. What is polarity? What does it mean to be polar? Is the Earth polar?
Yeah.
The Earth is polar. We got a north pole, we got a south pole. So polarity just means you have two different sides, right? Okay, two different sides. Well, molecules can be polar. They can have a positive side and a negative side. Here's some examples of polar molecules: hydrogen fluoride, hydrogen chloride, and water. Water is polar. It's got a positive side to it and a negative side to it. This unequal electronegativity value, so these different electronegativity values create polarity, which creates a slightly positive region and a slightly negative region to the molecule. When that polarity exists, we say that there's a dipole. Let's break this word down. What does di mean, guys? It means two. And poles just means there's two separate sides. So a dipole exists when a molecule has both a positive and negative portion due to differences in electronegativity. In chemistry textbooks, you're going to see a couple of different ways to show electronegativity or to show polarity, or a dipole. One of them is a dipole moment arrow. In your notes, I think you're supposed to draw a dipole moment arrow. So take a second, it's just an arrow, but on the tail side it has a little plus sign. On the tail side it has a little plus sign. And I want you to write in this: a dipole moment arrow always points to the more negative side of the molecule. And so the tail is slightly more positive. Now this was a little bit confusing until I started noticing something. This arrow with the little tail on it right here, it forms a plus sign. Well, that reminded me that it's the positive side. It always points to the negative side, but because there's a little plus sign here, that reminded me that's the positive side of the molecule. So that's one way that chemistry textbooks will represent a dipole or polarity in a molecule. Another way they do it is with this little sign down here. It kind of looks like a little S, but the tail is connected. This is a Greek letter. It's sigma. Okay? So some chemistry textbooks will write a sigma plus for the slightly positive region and a sigma negative to represent the slightly negative region. We're going to do it both ways so that you get used to seeing it both ways. Here's an example of what I'm talking about. If we take hydrogen fluoride, two nonmetals, so it's got a covalent bond between them. We said that in covalent bonds they share the electrons between them equally, but it's not true. We just learned that because of differences in electronegativity values, they don't share them equally. So this line right here accounts for 2 electrons that they share between them. Let's figure out which one takes and attracts those electrons a little stronger. I want you guys to tell me the electronegativity value for hydrogen. So grab your periodic table. What is it for hydrogen? 2.1. So let's write that in. What is it for fluorine? 4.0. Now, these 2 electrons in this bond are going to be more close to the hydrogen or fluorine? Fluorine, because it has a higher electronegativity value, right? So it's pulling the electrons more strongly to the fluorine, and so when you draw your dipole moment arrow, that arrow's got to be pointing to this side of the molecule, toward the fluorine. That means the hydrogen is slightly positive, the fluorine is slightly negative. We can write our sigma sign. Sigma positive for the slightly positive, and the sigma minus for the slightly negative. Okay. All right, I've got a number of practice problems so that we can get used to this. Okay, so let's get there. Practice problem number 1. It says, for the following molecule, label the electronegativity values for each atom, then draw the dipole moment arrow. So let's do this one together. Let's do the electronegativity values first. What is it for hydrogen, guys? 2.1. So in your books, on your notes, I want you to write that. 2.1, right by the hydrogen. What about bromine? What is it? 2.8. Now, obviously, which one's higher? The bromine is. The 2.8 is larger. So what does that mean? Is it attracting electrons more strongly or more weakly? More strong. So which side is going to be more negative? The bromine. Because electrons, which are negatively charged, are being pulled more closely to the bromine. So when you draw your dipole moment arrow, all you have to do is remember it points to the negative side. Okay, put your little tail on the end there, that's a positive. And let's also do the sigma sign. Which one's slightly positive? Okay, the hydrogen's slightly positive, and the bromine side is slightly negative. Okay. That's all you have to do there, guys, is draw the dipole moment arrow and list the sigma positive, sigma negative. Let's see if you guys can do one. Okay, so what I want you to do is to help me through this. Again, we're going to put the electronegativity values on each atom. Then we're going to draw the dipole moment arrow. Okay, so let's do it. What is hydrogen here? 2.1. Again, this is a hydrogen, 2.1. What about the chlorine? 3.0, and this chlorine is 3.0. And what about the carbon?
2.5.
2.5. Now, this one's a little bit different. It's not a linear molecule. What structure would this be? What geometry would this be? It's got 4 atoms attached to a central atom. What is it? Tetrahedral. Good. It's a tetrahedral molecule. So these are a little different. Let's look at it. Okay. Which way would the arrow be drawn here? Which one's higher? Towards the carbon. So it's going to go toward the left, toward the carbon, so it's toward the right. What about this one? Toward the carbon, so it's going to go up. What about this one? It's going to go toward the chlorine because that's higher. So we got another one that's going up. What about this one here? Yeah, 3 is greater, so it's going to go toward the right. So we got another one to the right. But here's the catch. You can only draw the arrow pointing in one direction. So which way should we go? Yeah, we kind of average it out. So this thing is going to go between them. And so when you draw your dipole moment arrow, it should be pointing up and to the right. Okay, which side is slightly positive? Well, the slightly positive is by the tail, the slightly negative is by the arrow. So if I asked you this, these hydrogens are going to be slightly positive or negative? Yeah, this side of the molecule is slightly positive. What about this side? Slightly negative. Is this a polar molecule? It is. It's got a positive side and a negative side. So there's our pole. It's a dipole.
So wouldn't you just be able to so hydrogen, lithium, they're all +1, and then over there they're all -1, or whatever. If they're plus or minus, can you just use that to do it instead of the value?
Yeah, you can. You kind of can. Remember the trend in electronegativity, guys. As it goes to the right, it goes larger, and as it goes up, it gets larger. So remember that electronegativity trend. It will help you. Yeah, you kind of can use that. Okay, let's go to practice problem number 3. I want you guys to try this one on your own. What I'm looking for is numbers, the electronegativity values by all these atoms, and then determine which way you should draw your dipole moment arrow. Okay, so let me give you a second. If you're watching the video, please hit pause and try it first. Let's see if you can get it right. Okay, guys, let's see how you did with this one. Hopefully, by the hydrogen is 2.1, so you wrote 2.1 as an electronegativity value. This one's 2.1 as well. What about the oxygen? Well, it's 3.5. Okay, now electronegativity is talking about these electrons that are shared in this covalent bond. This line accounts for 2 electrons. Are they going to be closer to the oxygen or to the hydrogen?
Oxygen.
Toward the oxygen. So we're going to get it's going to go up and to the right with this bond. What about this bond, though?
To the left.
Yeah, since the 3.5 is higher, it's going to go up and to the left. And so it's going to look like that. But when I draw the dipole moment arrow, it can only go one way. Which way should I draw it? Yeah, it's going to be the average between them. It's going to go up. So when you draw it, hopefully you drew yours like this. This side slightly positive. This side slightly negative. Okay? So if I ask you on the test, and I will, on a water molecule, these hydrogens are slightly what? Slightly positive. The oxygen is slightly negative. Okay, and I hope that you're seeing why water is attracted to water. Okay? If I draw a water molecule here, this water molecule, and let's draw another one here. Why is this water molecule attracted to this one, guys?
Hydrogen and oxygen want each other.
Good, because this oxygen is slightly negative, and this hydrogen is what? Slightly positive. And opposite charges do what? Attract each other. So there's this force of attraction right there. It's called an intermolecular force that's pulling them together. It really is just like little mini magnets. Molecular magnets. Okay, and that's why water loves to stick to water. That's why you see rain follows water droplets. It's not just a flat, they're attracted to each other. There's cohesion. That's what we call it. Okay, practice problem 4. Let me go through this one with you.
Yes.
Okay? So, let's find the electronegativity values. What's chlorine?
2.5.
Chlorine is what?
Oh,
Isn't it 3.0?
yeah.
Okay? This one's chlorine, so it's the same, and same. Okay, now let's just look at it. Oh, carbon is what?
2.5.
2.5. Okay. Now, the electrons are going to be pulled closer to the chlorine or the carbon? To the chlorine. So, I'm just going to draw the arrows here. It's going to go to the left on this bond. Let's look at this bond now. Which way?
Up.
Up. Okay, so it's going up. What about this bond?
Right.
The electrons are getting pulled toward the chlorine, so it's going to go toward the right. And what about this bottom one? It's going to be pulled toward the chlorine, which is down. Now, we can only draw one arrow, and that's if we draw an arrow at all. Okay? Doesn't this 3.0 and this 3.0, don't they get canceled out?
Yeah.
Okay, left and right, yeah, there's no net pull of electrons. They're kind of canceling each other out. And can't we say the same thing down here and down here and up here?
Yes.
Yeah, so they cancel each other out. So this molecule, is it polar?
Nope.
It's not.
Right.
And so let's just write non-polar. So this is a nonpolar molecule. If you had another one of these molecules and put it by this one, would it be attracted to it? There would be no attraction there. They don't want to stick together. It's nonpolar. Okay, so it wouldn't stick together like water would. There would be no cohesion with this molecule. Okay, very good. Let's go to practice problem number 5. I'll give this one away. This is a polar molecule. I want you to show me which way the arrow, the dipole moment arrow, would point. I want to give you a second to try it on your own. So please hit pause and try it. Okay, guys, let's see how you did with this one. By hydrogen, hopefully you wrote 2.1. That's its electronegativity value. And since we have these other hydrogens, that's easy, 2.1. Now the nitrogen is what, guys? 3.0. Now, I'm going to draw the nitrogen, and let's do the arrow thing again. Which one is the electrons going to be closer to, the hydrogen or the nitrogen? To the nitrogen. So it's really going to pull toward, well, actually, let me put it this way. It's going to be pulled toward the nitrogen, right? So let's go this way. Okay, what about this bond? Toward the nitrogen, so it's going to go toward the nitrogen this way. And what about this bond? Toward the nitrogen. Okay. Now, these are called covalent bonds. They're shared between two different atoms. What did we call these electrons? It's called a lone pair. This is called a lone pair. And they're not being shared, so we're just going to leave them there. We don't actually do anything unless it's a covalent bond that's shared between two atoms. So that's it for as far as the arrows go. So which way would you draw the arrow? Up. Yeah, it should go up. The left and right kind of cancel each other out, don't they? And so now we've got just this one arrow. So I would draw the arrow like this, slightly positive down here, and slightly negative on the top. So that molecule is polar, and there's how you draw the dipole moment arrow. Okay, I've got one more for you real quickly. I want you guys to try this one on your own. Again, if you're watching the video, please hit pause and try it first. Okay, let's see how you did with this one. Oxygen, what's its electronegativity value, guys? 3.5. So that means this oxygen is also 3.5. What's carbon? 2.5. Okay, so if I draw the central atom right here, again, it's carbon. In this double bond, are the electrons going to be pulled closer to the carbon or oxygen?
Oxygen.
Toward the oxygen. So the electrons are going this way. What about this double bond? Toward the oxygen. Yeah, because 3.5 is bigger than 2.5, so they're going to go toward the oxygen, so it's going to go this way. What do you say?
No polarity.
No polarity. Yeah, this is going to be canceled by this side. So this molecule is what? Non-polar. This is a pretty famous molecule as well, carbon dioxide. So if I had another carbon dioxide molecule here, will they be attracted to each other? No, there's no attraction there because it's non-polar. Okay, very good. All right, that's one way to determine whether a molecule is polar or not. But what I'm going to go over now is another way. Okay, and we're going to use it a lot in this chapter, so let's look at that one. Jared.
So are gases non-polar then, because they always spread out? Like,
yeah, gases are more non-polar. Yeah, they have more non-polar characteristics. Yeah, good observation there. Okay, let's learn the next way to determine whether a molecule is polar or not polar. Okay, there's a few steps that we have to take with this method. Number one, you have to be able to draw the Lewis structure. I know it's been a few chapters, a couple months since we've done this. So I'm going to help you review it through this video. Step number two is we're going to determine if the molecule is symmetrical or asymmetrical. So we're going to check for symmetry. What does it mean to be symmetrical, guys? It's the same on both sides, so there's a mirror image. Give me an example of something that is symmetrical. A square, is it symmetrical? If you cut a square in half, is it the same on both sides?
Yes.
Absolutely.
Rectangle.
Rectangle, same thing, right? Okay, so symmetry, so if it's symmetrical, it's got a mirror image. What does asymmetrical mean? It means they're not mirror images. You can't fold it in half and have it be the same on both sides. So we're going to look for that. Okay, and here's the deal. If there is symmetry, so if it is symmetrical, it has to be symmetrical in every direction. Not just up and down, but it has to be left and right as well. If there's symmetry in every direction, then it's nonpolar. Now, if it's asymmetrical, the molecule will be polar. Okay, and this always confuses people. So there's an easy way to remember this that's taught in almost every chemistry textbook. Yeah, this is a good acronym to learn. It's called SNAP. Okay? So we're going to use the SNAP acronym to remember. An acronym, guys, uses a letter to stand for something. So this S stands for something. This N stands for something. The A and the P also stand for something. Let's learn what it means. Okay. Symmetrical. If it's symmetrical in every direction, the molecule will be nonpolar. So in SNAP, the S means what? Symmetrical. The N is nonpolar. Okay. However, if the molecule is asymmetrical, it will be polar. And so this A in SNAP stands for what? Asymmetrical. And the P for polar. Okay, one more time. Let's go through it. What does the S stand for? Symmetrical. Nonpolar. Asymmetrical is polar. Now, if there's symmetry, does it have to be in every direction? Yes, it does. It has to be symmetrical in every direction for it to be considered nonpolar. All right, let's try a practice problem and see if we've got this. Okay. Number 7. It says to draw the Lewis structure for the following molecule. So we need to do that first. And then we're going to use SNAP to determine whether it's polar or nonpolar. Okay. So let's review Lewis structure. First step is to count the valence and add it up for the whole molecule. So the total valence in this molecule. How many valence from hydrogen? 1. But how many hydrogens do I have? 2. So we're going to times it by 2. And then we're going to add in the valence for this oxygen. How many valence for oxygen? 6. So that's 2 plus 6 for what? 8 valence electrons. Please write this in your notes. Okay, it's going to help us remember. Now, second step is to decide which atom goes in the middle.
Oxygen.
Does hydrogen ever go in the middle? No, it will never go in the middle. So let's write oxygen symbol and draw how many dots around it? The 6 dots. It's got 6 valence. So every dot represents 1 electron. We're just going to go clockwise and put 1 on each side until we get to what? Until we get to 6. Okay, so there's my 6 dots. It's 6 valence. Where do you think the 2 hydrogens are going to go? Yeah, I can only go where there's an opening. Okay, and this has an opening. How many electrons does the hydrogen bring to share? 1. Okay, so bring its 1 electron. Now, there it is. Do I have 8 electrons?
Yes.
2, 4, 6, 8. We do. Can I just be done?
No, you got one.
No. If it is a shared pair, so what I mean by that, if there are 2 electrons between 2 separate atoms, it's called a covalent bond. And how do chemists represent covalent bonds? A line. Okay, so we're going to write it like this. Do I still need the lone pairs? Yes, you still need the lone pairs. So when you write it like this line accounts for how many electrons? 2. So there's 2, 3, 4, 5, 6, 7, 8. Do I have all 8?
Yes.
Yes. Okay, so what we just did there was draw the Lewis structure for water. Now, let's use snap to determine whether it's polar or nonpolar. Okay, if I was to imagine a line right here, is it symmetrical down this axis?
No.
It's not, because this hydrogen on the left, there's not a hydrogen on the right to make a mirror image. So it's not symmetrical. What about this way?
No.
It's not. Again, because the hydrogen and then there's not a hydrogen here, so it's not symmetrical. If it is asymmetrical, what does that mean?
It is polar.
It's polar. So all we have to do is put polar. And water is a polar molecule. Good job. I've got a couple more. Let's see if you guys can do this. So I want you guys to try this one on your own. Okay. Again, draw the Lewis structure. Then use snap to determine whether it is polar or nonpolar. So give it a shot. See if you can get the answer right. All right, guys. Let's see how you did with this one. Hopefully, by carbon, how many valence does it have? 4. Hydrogen has 1 valence, but we got 4 of them, so I'm going to times it by 4. What's 4 plus 4, guys? 8 valence electron total in this molecule. Which element's going to go in the middle? Carbon. So I'm going to draw carbon. How many dots around it? 4 dots. 1 on each side. Now, the 4 hydrogen here, where are they going to go? Oh, on each side. It brings 1 electron to share, because it has 1 valence. Okay, and all of these electrons, aren't they shared pairs? So they're involved in covalent bonds. So when you draw it, the chemist would draw it like this. Now let's check my electrons. Each line accounts for 2, so there's 2, 4, 6, 8. I've got all 8 of them. And they're all obeying the octet rule. So now let's use snap to determine whether it's polar or nonpolar. If I imagine an axis right here, would it be a mirror image on the left and right? Guys? It is a mirror image, isn't it? Yeah, this hydrogen are a mirror image of each other. What about this axis?
It's symmetrical.
Is it symmetrical? It is. And so it's symmetrical in every direction. What does that tell us? That it's nonpolar. Okay. How many of you guys got that one right? Okay, very good. I've got one more problem. Okay, let's see if you can do it. So again, try this one on your own. Draw the Lewis structure, then use snap to determine whether it's polar or nonpolar. So please hit pause and try it on your own first. All right, let's see how you did. Nitrogen has how many valence, guys?
5.
It's got 5. What about the hydrogens?
1.
It's got 1, but how many do I have? 3. So what's 5 plus 3? 8 valence electrons. Which one goes in the middle? Nitrogen. Hydrogen never will. So let's draw 5 dots. 1, 2, 3, 4, and 5. Okay, now the 3 hydrogen, I hope that you can see where they've got to go. But they bring 1 electron to share. Now, we have to draw lines for the covalent bonds. So let's do that. Now, what about these electrons at the top that are not being shared? What are they called again, guys? Lone pair. That's a lone pair. And so we just leave them as dots. Okay, do I have 8 electrons? Well, I got 1, 2, 3, 4, 5, 6, 7, 8. Are they obeying the octet rule?
Yes.
And yes, it is. So now let's use snap. Guys, imagine an axis right here. Is it a mirror image? Is it symmetrical this way?
Yes.
It is. But what about this way?
No.
It's not. Okay, it's not symmetrical that way because this hydrogen, there's not a mirror image of it over here. And so if it's not symmetrical, we say that's asymmetrical, which means what, guys? It's polar. Okay, very good. I hope that you have I hope that you guys have learned the difference between polar molecules and nonpolar molecules. I hope that you have learned why molecules are polar, and it's because the differences in electronegativity values. I hope that you have learned if the electronegativity value is higher, it pulls electrons toward it more closely. And because electrons are negative, that would make that side of the molecule more negative. Okay? So, to give you some more practice, in your student workbook, there is a worksheet, and it's titled Polarity Worksheet. So I'd like you to go to your student workbook. Again, it is called Polarity Worksheet. And let's get that completed. Okay? And hopefully this video helped.